Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh to all my panels. I am NUR AMIRAH BINTI MOHAMAD ZEN. I am a final year student of School of Mechanical Engineering from College of Engineering UiTM Shah Alam. My supervisor is Dr. Alhassan Salami Tijani, who supervised me throughout this semester. So today I'm going to do a presentation for my final year project with the title of Numerical analysis of bubble evolution and convection transport mechanism effect on the operating voltage and efficiency estimation of polymer electrolyte membrane electrolysis. So let's proceed with the explanation. First, I'm going to explain about the introduction of this project that consists of project background, problem statement, objectives, and scope of works. Starting with the project background, like how this idea of doing research on hydrogen production using PEM electrolysis came up. So recently, the rate of growth of world human population keeps on increasing, which has led to a huge demand of global energy. Global energy is the energy that will not just help in sustaining human lives, but also to sustain electricity, transportation, residential sector, and industrial sector. But one of the main concerns throughout the years is the environmental issues that occur recently. This is because the energy production is mainly dependent on fossil fuel, and due to uncontrolled use of fossil fuel such as natural gas, oil, and coal, it has caused a huge amount of carbon dioxide emission that will eventually lead to global warming. And that is why the application of water electrolysis process was chosen for further research in hydrogen production. But why water electrolysis? This is because among all methods used to obtain hydrogen, water electrolysis is one of the safest methods as it is eco-friendly, which means it will bring no harm to the environment. And there are many kinds of water electrolysis, but why I chose PEM electrolysis is because it has high pure efficiency as it will only emit oxygens without any carbon emission. And PEM electrolyzers are also known with its advantages that is less caustic, which means it causes less damage caused by chemical action, and it can be a reversible device. It also has a reliability, which is high reliability and high durability, and it can work with high efficiency for about 80% to 90% efficiency. Just a little bit continuation from the project background. We want to know why we choose hydrogen. Out of all elements, why we choose hydrogen? This is because it is not just the most efficient energy carrier and can be obtained from any kind of sources, but hydrogen can also be an alternative fuel, and it also only emits oxygen during the production of hydrogen, and there will be no carbon emission. So, the issues of global warming can be reduced. As mentioned before, PEM electrolysis is known with its high reliability and high durability system. But to provide a system that can maintain its good performances, it will cost an expensive amount to develop the system, especially in providing the best components. For example, the material used for the electrodes are usually made of an expensive group of metals such as platinum, iridium, or even ruthenium that is classified as the rarest element in Earth crust. Instead of material of the electrodes, the system also requires a thick polymer electrolyte membrane and metal collectors and bipolar plates that are corrosion resistant, which makes the whole system too expensive for the industrial application. Another factor that contributes high cost to the system is high energy demand. This is because PEM electrolyzers are mainly operated based on electrical energy sources. That is why electrolysis process, especially hydrogen production for a large-scale industry, require high amount of voltage that is known as overpotential to operate the system. So, if we cannot provide the best components and enough energy to operate the electrolysis process, then it will provide a low efficiency system of water electrolysis. Next, there are three objectives that need to be achieved in the project, which is the first one is to investigate the effect of different values of current densities to the operating voltage. Second, to analyze the effect of different temperatures to operating voltage. And third, to evaluate the effect of operating voltage to the efficiency of the PEM electrolysis. After that, let me explain about the scope of this work. All simulation to obtain the results will be conducted using MATLAB software, and operating parameters are evaluated at low temperature, which is in the range of 20 degrees Celsius to 90 degrees Celsius and at 1 atmospheric pressure. Next, I will proceed with the literature review that consists of thermodynamic modeling of PEM electrolyzer, performance evaluation, and characterization of operating parameters for PEM electrolysis. Operating voltage in PEM electrolysis is a summation of four mean voltage that is known as reversible voltage, activation over voltage, ohmic over voltage, and diffusion over voltage. But diffusion over voltage is usually negligible for the simulation, since the temperature has no influence on the value of diffusion over voltage. And there is also an additional overvoltage introduced in this study, which is bubble overvoltage, that is used to evaluate the effect of surface blockage by the bubble on the performance of the electrolysis process. And all the equations used in the simulation are shown in the slides. There are five main components that will be evaluated in the performance evaluation of PEM electrolysis, which is hydrogen production, charge transfer coefficient, power consumption, and as shown in the slides as input power, and efficiency performance estimation that will be evaluated from energy efficiency of PEM electrolysis. So in the slides, it shows the equation used for evaluating each parameter for the study. The last part in literature review is the characterization of operating parameters for PEM electrolysis. So the table shown is the list of parameters of exchange current density, operating temperature, charge transfer coefficient, and electrode properties that were obtained from different journals that I referred throughout the study. Next, we will proceed with the methodology of this project that consists of mode of operation of PEM electrolysis, schematic diagram of PEM electrolyzer, and system integration of PEM electrolyzer. Starting from mode of operation of PEM electrolysis. So, PEM electrolyzer is known as a device that is used to split the molecules of water into hydrogen gases and oxygen gases. The electrolyte used for PEM electrolysis is the membrane itself that can be seen on the slide, which is at the center, that is sandwiched between anode electrode and cathode electrode. Both electrodes are attached to the bipolar plates that have channels for water and gas to flow through, and both are connected by the external cell voltage to allow the electrons to flow. Starting from the anode side on the left, water reacts at the anode to form oxygen and positively charged hydrogen ions, and the hydrogen ions will flow across the PEM to the cathode. Then at the cathode side on the right, the hydrogen ions will combine with the electrons from the external circuit to form hydrogen gas. Next is the schematic diagram of PEM electrolysis that consists of PEM electrolyzer, heat exchanger, and also separator that is used for hydrogen production. And there are also three types of gases generated when the process started, which is hydrogen gas that will flow out from the cathode electrode and oxygen gas that will flow out from anode electrode. The mixture flow of hydrogen gas and oxygen gas that will flow out from the outlet of PEM electrolyzer will be separated and will be cooled down to the reference condition after leaving heat exchanger 1, as you can see on the slides, while water from the mixture flow will return to continue with another process of hydrogen production at elevated temperature or hot temperature after flow through the heat exchanger. And heat exchanger 2 will help to heat the water that flow through it before it reaches the temperature of PEM electrolyzer. The last part in methodology is system integration of PEM electrolyzer. So the process starts when the water is supplied from the water tank and enter the channel of bipolar plate at anode side and undergoes electrokinetics when the electricity is supplied externally. So the electricity supplied will help to split the water molecules into hydrogen ions and oxygen gases, where the oxygen produced at the anode side will escape to the surrounding, and the hydrogen ions will be transferred to the cathode side through the membrane together with the electrons supplied from the external circuit. Moving on to the cathode side. So the hydrogen will be produced due to the interaction between the hydrogen ions and electrons. So the hydrogen at the cathode side will flow through the bipolar channel and collected in the hydrogen storage tank. Moving on to the last section of this project, which is the results and discussion. The first two analyses was done on the parameter involved in ohmic overvoltage, as ohmic overvoltage is influenced by the resistance caused by the electrodes and ionic conductivity through the membrane in the PEM electrolyzer as shown in figure A and figure B. So in figure A, it shows that when the temperature increases, the membrane conductivity will also increase, while at figure B, it shows the opposite results as the value of ionic resistance drops when the temperature rises. So this is because when the temperature increases, the reaction rates at the electrodes will also increase and cause the membrane water activity to amplify in order to produce a better conductivity. While in figures C and D, it shows that both ohmic overvoltage and activation overvoltage decrease when the temperature increases, but the value drop at ohmic overvoltage is very small compared to activation overvoltage. The decrease in the value of overvoltage due to the increase of temperature is because the electrokinetic of water is enhanced at high temperature that will cause a faster reaction at both electrodes, thus reducing the voltage. Next is the comparison of anode activation over voltage and cathode activation over voltage that was made on the lowest and highest temperature, which is 20 degrees Celsius and 90 degrees Celsius, that can be seen on figure A and figure B. So it can be observed that the value of anode activation over voltage is higher compared to cathode activation over voltage. This is because the energy required to initiate the electrokinetic process at anode is higher than at cathode. Anode electrode require more energy, which is used to split water into hydrogen gas and oxygen gas. While at cathode side, the hydrogen ion and the charge of electron is already reacted without require any external influence. So that is why less energy needed at this side of electrode. Then moving on to figure C, it shows that the value of operating voltage decreased when the temperature increased from 20 degrees Celsius to 90 degrees Celsius as the voltage drops in the process, which lead to a better performance of PEM electrolyzer. This is because increase in temperature causes the electrochemical reactions become faster in the process, that will increase the value of exchange current density and eventually lead to less voltage drop. While in figure D, although the irreversibility in PEM electrolyzer are contributed by four main overvoltage, which is anode activation overvoltage, cathode activation overvoltage, ohmic overvoltage, and reversible voltage, but the value of anode activation overvoltage is still the highest, because anode activation overvoltage is the dominant cause of the irreversibility in PEM electrolysis. Next is the study of effect of CTC on performance of electrolysis cell. So in figure A, it can be seen that the CTC value at anode are significantly increased higher compared to cathode CTC value. This occurred due to high dependency of anode reaction mechanism to the temperature. This is because CTC at anode has more influence to the kinetic reaction in the electrolysis process that is used to split water into hydrogen gas and oxygen gas. Moving on to figure B, C and D, which are the simulations made on the effect of multiple value of CTC on activation over voltage. In general, it can be summarized that activation over voltage decrease when CTC increase as plotted in the figures. And the value of activation over voltage at both anode and cathode are the highest, which is 0.8374 volt and 0.4143 volt respectively, at the lowest value of CTC, which is 0.2. So this is because CTC is known as the fraction of potential energy that is applied to the electrochemical reaction, and it will cause the reaction rate in the electrolyzer to increase. Therefore, when the value of CTC increase, less amount of activation over voltage required by the reaction electrokinetic occur at the electrode. Next is the effect of CTC on performance of electrolysis cell, but this time with different value of CTC. So the simulations discussed about how CTC affect the activation over voltage, where the evaluation was made for CTC in the range of 0.5 until 2.0 for anode and 0.1 to 0.4 for cathode. The reason why the range value of cathode CTC is lower compared to anode CTC is due to less electrochemical activity required at cathode side. So in general, it can be summarized that activation over voltage decrease when CTC increase, where it can be seen at anode and cathode at both lowest and highest temperature. For example, at highest anode CTC of 2.0, the value of activation over voltage remains as the lowest at both temperature. And the same thing occurs at cathode side, where at the highest cathode CTC of 0.4, the value of activation also considered as the lowest at both 20 degrees Celsius and 90 degrees Celsius. Next is the effect of exchange current density to the performance of electrolysis cell, which has been done to all temperature 20 until 90. It can be stated that CTC decreases when the exchange current density increases at both anode and cathode electrode. And another observation that can be concluded from the graph is anode CTC seems to have higher value compared to cathode CTC. And the simulation for 80 degrees Celsius and 90 degrees Celsius are shown in the next slides. This is the continuation from the previous slide. So the same thing occurs here as CTC decrease when exchange current density increase at both anode and cathode electrode. This is because since the exchange current density in PEM electrolyzer act as a measure of the electrode kinetic reaction, the results can be indicated that when the exchange current density increase, it will enhance the electrochemical kinetics reaction at the electrodes. So the CTC value required for the kinetic rate of reaction at the electrolyzer is lower. Next is the effect of temperature on energy efficiency. This graph evaluates on how efficient the water electrolysis works as the temperature and current density increase in the electrolyzer. And as obtained on the graph, the energy efficiency of PEM electrolysis keeps on increasing when the temperature rises. The high efficiency of water electrolysis shows most of the energy in the process are used for decomposition of hydrogen and oxygen, while low efficiency shows that some of the energy are lost as heat during the process. Next is the results of effect of input current and input power on hydrogen production rate. So in table E and table B, It shows that the evaluation of percentage error of hydrogen production rate, since there are some differences in the theoretical and experimental values. So according to few journals, there are a few reasons why there are some difference occur on both theoretical and experimental values of the hydrogen production rate, where the first reason is due to measurement errors that is caused by sensitivity of measurement, or there are also might be a leakage of hydrogen in the PEM electrolyzer that may occur during the process. The results of both theoretical and experimental values can be considered as acceptable since the value of percentage error does not exceed 20%. The last one is the study on the effect of fraction surface block on the electrode on bubble over potential. In general, it can be summarized that bubble over potential increase as the temperature increase. And when comparing anode and cathode bubble over potential, even though with the effluent of CTC, cathode bubble over potential is higher compared to anode bubble over potential. This is because, according to a few journals, this occurred due to the direct relationship between bubble over potential and temperature in the equation used. And the fraction of surface block also has high influence on the PEM electrolyzer performance. This is because the bubble formation that covered the electrode can cause loss of overpotential, as the area that was covered by the bubble is considered as inactive surface. So higher utilization factor of overpotential required at the covered area to continue the electrolysis process. From the results, it can be concluded that PEM electrolyzer work best at high temperature, high current density, low exchange current density, and high charge transfer coefficient. This is because at a high operating temperature and low exchange current density, high value of CTC will be produced. Thus, it will lead to decrease of overvoltage in PEM electrolyzer. And if we want to consider the effect of bubble formation, some recommendation can be suggested for a better performance, which is control the value of operating temperature and also CTC. This is because at high operating temperature, high CTC will be produced. Thus, it will lead to high fraction of surface block and high bubble over voltage in PEM electrolyzer, so it will distract the performance of PEM electrolysis. Okay, I think that is all from me. If you have any question regarding my presentation, you can ask me directly through my email address at amirahmohammadzen@gmail.com, or also through my phone number 019-753-8454. Thank you for your time. Have a nice day. Assalamualaikum.